Hello, everyone. Welcome to Foresight Space Group. Today, we're joined by Garret Fitzpatrick. He's the principal investigator and project engineer at the Smithsonian Astrophysical Observatory. Formerly, he was a systems engineer at NASA Ames, and he was a crew survival system manager for 15 Space Shuttle missions and flight at NASA Johnson. And today, he'll be presenting to us an Earth-sized telescope and an arc on the moon. So thank you so much to Garret for joining us.
All right. Thank you for having me. Good morning, good afternoon, good evening, wherever you might be in the world. I'm really grateful to talk to you today. As Lydia mentioned, I'm Garret Fitzpatrick. I'm a systems engineer and principal investigator at the Smithsonian Astrophysical Observatory, which is part of the Center for Astrophysics at Harvard and Smithsonian. And today I'm going to talk about three things: black holes, the moon, and impossible challenges. And more specifically, an Earth-sized telescope, a backup of Earth's life designed to last for more than 1,000 years, and why we need impossible now more than ever. Black holes and the moon may not naturally go together, besides the fact that they're both in space, but I'm going to try to connect these two together around a deeper idea. And that idea is something I'm calling the impossibility frontier. It's something of a modern reframing of an old idea about frontiers, and it's one that I believe is essential to how we think about growth and innovation in our culture. Let me start with black holes. I'm going to guess that everybody in the space seminar group probably has seen this before. This is the first image of a black hole. This was the black hole in the center of galaxy M87. It was released in 2019. It's about 55 million light years away. And I joined the team in 2020, so I take no credit for this image. My role is as the project engineer for the next generation Event Horizon telescope. So we're designing a transformational upgrade to the array that produced this through the Event Horizon telescope. Of course, the image of a black hole was quite sensational. It appeared on the front page of most major newspapers all over the world. And so when we think about it, why was it such a breakthrough? First of all, light can't escape a black hole. It's a black hole. How do you see the unseeable? Second, it's a whole new laboratory. It's giving us really a whole new field in astrophysics, giving us a glimpse into some of the most enigmatic, mysterious, and energetic objects in the entire universe that we know about. And to do it, to image it, requires a facility that has the highest angular resolution of any astronomical facility. And to make that happen, you need a telescope the size of the Earth. So all these things together make for a pretty compelling story. I'm not going to go into too much of the science behind the Event Horizon telescope. I'm going to focus a little bit more on the next generation and the things we're doing and how we're designing the array. But I think it's important to think about what we're actually looking at. So I'll do a quick primer here. Of course, black holes are immense. The gravity is so immense that even light can't escape, and it's affecting and modifying the fabric of space-time around the black hole. I think the best way to imagine what we're actually seeing is to think about the paths of light through photons as it's coming to the observer. So light, as it's going around, it's curving. Some of it is curving a little bit and heading off into space. Some of it is making a complete orbit before it comes to us. And some of it is trapped forever in what we call the photon ring. And so what we're seeing is a composite of photons and the accretion disk around the shadow of a black hole. So
hey, Garret.
Yeah.
We get something about this though. These are millimeter wave telescopes, right? So we're not really doing what we think of as light, even though it is electromagnetic radiation.
That's right.
And also another question, which maybe you can clarify. People talk about the photon rings, but obviously we can't see the photon rings because that's light that's trapped in an orbit, not heading to us. So how can you explain at some point the relationship of these kinds of pictures to light and photon rings?
Yeah, so I think what you're really seeing is the photons that are reaching us, and those are the ones that, if I play this again, this is the best way to imagine it, is what a lot of this light is making many passes around the black hole before it reaches us. We're seeing what's making it to us, and it's being lensed around the shadow of the black hole. I don't know if that answers your question, but what we're actually seeing is what's coming to us as an observer. All right, that's a little bit of a primer. What we've been able to image so far are these two black holes. So this is, on the left is the black hole in the center of galaxy M87. It's larger than our solar system. It's changing fairly slowly, especially compared to the one on the right. This is the black hole in the center of our galaxy called Sagittarius A star. This one is spinning on the order of minutes to hours, whereas the one on the left is changing on the order of days to weeks. But they both are roughly the same size on the sky. So they're around 40 to 50 microarc seconds. This is about 10 billionths of a degree. So very small. They're very large, but they're very small on the sky. And this just so happens to correspond to the same size dish that you would as the Earth. The angular resolution is related to the wavelength over the diameter. Larger dishes help you see very small. We know we're limited in the radio regime here because you have to see through all the dust and gas between us and the center of galaxies where these supermassive black holes are. So we're limited to about a millimeter in wavelength, and that corresponds to the size of the Earth. We can't build a telescope that big, obviously, but what we can do is connect telescopes together and then bring the data back to a central correlation facility. And this is called Very Long Baseline Interferometry. Back in 2018, this is what the array looks like. And it's also crucial to point out that the Event Horizon Telescope was pulled together from existing telescopes that for most of the year are doing other science. And for about 2 weeks out of the year, we point them in the same direction and they come together as part of the EHT. So other telescopes include sites in Hawaii, in Arizona, Mexico, in France, in Chile, in Antarctica, and Greenland. And the other aspect is we're able to take advantage of the rotation of the Earth. And I don't know, this is not changing. Okay, so I don't know, something might be wrong with the animation here, but what we're doing is we're taking advantage of the fact that the Earth is rotating. We're taking the data as collected. Every point, every two sites form a baseline, and those, as the Earth is rotating, it's tracing a path in the UV plane. So we're actually taking data, not just in a snapshot, but we're tracing a path, and we're taking that data and then creating an image from it. Okay, so what's next? Next up is movies of black holes, the first ever black hole cinema. The EHT is going to be able to do this in the next few years. If you think of what a movie is, it's a series of frames. But when we talk about next generation goals and science goals, we need a transformational upgrade, new sites and new capabilities. And so what in new science we're trying to do is we're trying to detect dozens of new black holes. Right now, the EHT can observe other black holes, but it can't image them yet. So we want to open up the parameter space there. We want to be able to measure the spin of supermassive black holes. This will allow new tests of general relativity. We want to be able to understand how these relativistic jets that are sending material at near light speed across entire galaxies, we have very little idea of how they're powered. We've never really seen the connection between the horizon and these large-scale structures. So we want to be able to see that. And then it's also a discovery instrument. So we want to be able to understand exotic phenomena that we might not expect. So why can't the EHT do this today? Why do we need to design anything? On the right are images from 2017 and 2018. And what we think M87 looks like on the left. And we're limited in a number of directions. One is field of view. So we want to be able to expand to be able to see these jets, both in the small and the larger scale structure. We're limited in resolution. Many people have pointed out these are fairly blurry. We want to get sharper images and understand the dynamics of what's rotating around, what's orbiting around the black hole, what's in the accretion disk. We also want to understand and expand the dynamic range to be able to see fainter structures like these jets. We can't see it now because our dynamic range is limited. We also want to expand the range of accessible timescales, both down to, on the order of seconds and longer up to the order of weeks and months. So we want to be able to observe every 3 days for 3 months at a time. And that'll drastically expand what we're able to learn. We're also not very sensitive to persistent structures, gravitational features around the black hole. We're limited, as I mentioned, to the number of sources as well. We have n equals 2 right now. And so we want to expand that to the next tier, which is going to give us on the order of tens of black holes that we can then image. All right, so how do we do this? This is where systems engineering can help. And this is in my role. I'm trying to lead the team through the design process and into implementation for these upgrades. I like to say that the role of the architect is reducing ambiguity, employing creativity in the design process, and also managing complexity. Early on, it's good to explore prototypes, science goals, imagining what's possible. Later on, we don't want that exploration. So this is why we apply processes like this in the design, diverging, converging, ultimately getting to something that we can build and do that, on schedule and on budget. A little bit more about the systems challenge. This is, in a lot of ways, the whole Earth is our canvas. We're looking for high and dry sites all over that can fill in the UV in kind of key locations. We know we're limited to radio because of what I mentioned with the dust and gas. And we know that we're not just building one telescope, but we're building many telescopes. On the input side, we're literally inventing some of the imaging, construction, the simulations. We're inventing that as we go. So those are changing. The parameters of the design space are changing. The data and calibration pathways are brand new. And again, we're on the output side, we're not just building one site, we're trying to roughly double the number of sites in the array. So that adds additional complexity. All of these sites need to interface with all of the existing sites of the array. And all of them were built to different requirements, different interfaces, built by different people with different stakeholders, and they're doing different science for the rest of the year. And the configuration is changing. So instead of just a single space telescope, you turn it on, it has its capability. The array configuration is changing over time and the performance is changing. And what you can achieve with that performance is also changing. So these are all just factors that we need to consider. And then we're talking about purpose-built VLBI sites, whereas the HT used existing sites, and 2 weeks out of the year, we're now talking about kind of purpose-building new sites that will be available and observing for most of the year. And those are owned and operated by different people with different standards and different environmental permitting, all of those things. The data challenge is also a large challenge. We're talking about on the order of 100 petabytes a year that we'd be collecting. We have to collect all of it, including the noise. We have to support it by airplane, correlate the data, calibrate it, and reduce it down to a 1 megabyte movie. So it's about 12 orders of magnitude in data reduction. So lots of challenges on the data side. I'm not going to read through all of these, but I often joke with my colleagues building space instruments that in a lot of ways, space is easier because you're constrained. Volume, mass, power, physical constraints of a launch vehicle, we're less constrained. And things like trying to understand robustness for design that has good weather at multiple sites for 3 months, every 3 days for 3 months out of the year simultaneously, right? This is not an easy problem to optimize for. And also you need to be robust against the dropout of many sites to design. Not to mention all the non-technical side, there's a lot, as you can imagine, building on the order of a $200 million project in an academic setting, very diverse and complex stakeholder landscape, and of course, with anything, lots of politics at play. It all adds up to what I like to say, it's an amazingly interesting challenge. And we're now coming to the end of this design process. So we've been at it since about 2020, and now we're at the point of implementation. So when we talk about what this array looks like, we're adding new sites. These are the new sites that we want to move forward with. A site in Wyoming, in Mexico, in the Canary Islands and in Chile, adding an existing telescope here in Massachusetts, the MIT Haystack. We've developed new backends that have wider bandwidth that increases the sensitivity of the array, new receivers that allow tri-band simultaneous observation, new antennas, and new correlation facilities. All of this is what we want to do. Funding landscape is not necessarily ideal right now, but we are moving forward with the first dish. This is the first new NGHT site, and we're working with our colleagues in Spain, in the Canary Islands, to design to start constructing this dish. We hope to start next year on the construction, and it would be ready in hopefully in 2028. Okay, so that's the NGEHT story. I'm going to move on to the next. We can come back for questions at the end. So the next piece of this is about the moon. This is a lunar biorepository project. And I like to start with this somewhat provocative question is, imagine the years 30, 25,000 years from now. How much of what we build today will still be around? This is a time scale that engineers, we don't often think about. We don't often think about materials or how we are going to communicate with humans 1,000 years from now. But these are all relevant when we start thinking about this project. The concept here starts with the Svalbard Global Seed Vault that you may have heard of. This is the Doomsday Vault, in other words. It's in Svalbard in Norway, and it has over 1 million seed samples from almost every country globally. It's a backup of crops, securing the genetic foundation for our future food supply. So in case there's an apocalypse and you're like one of the last humans alive, you need to like restart human civilization, you should know where this is. It's in Svalbard. This is very isolated. It's the farthest north that people can fly on a scheduled flight. It's buried in a mountain. It's geologically stable. And it also uses the permafrost as passive cooling as a fail-safe method, which is important when we think of this concept. Okay, so the Smithsonian is the largest museum and research complex in the world. We have other research units. We have at SAO, we happen to be involved in space and instrumentation. We also have groups like at the Conservation Biology Institute at the National Zoo that are thinking of cryobiology, and they convened a group across the Smithsonian and other institutions to ask this question: what could we do something similar for animal cells? Seeds only need to be kept at about minus 18 degrees Celsius. Animal cells need to get a lot colder, about minus 196. And it turns out that this, from just a temperature perspective, the moon is an ideal place for this. If you're talking about passive cooling, there are regions on the moon in these permanently shadowed regions that haven't seen sunlight in billions of years. They stay at this temperature or colder. So if you can get there and deal with the radiation, it could be a really compelling concept. I'm going to take a step back for a second just to talk about why would we consider the moon? Is the risk high enough to warrant taking extreme measures like this? There have been 5 major extinction events in Earth's history. Many scientists think we're on the cusp of number 6. They define major extinction event as the loss of more than 75% of species. And so we're actually not seeing, just in absolute terms, that level of species loss. But there's a lot of reasons to think that the actual rate is actually higher and it's accelerating. One of the things that tell us that is about population extinction. And this is something we're seeing: populations being decimated in many regions for many species. And this is all indicating that we're trending in the wrong direction. Not only is biodiversity at risk, Earth-based biorepositories are also at risk. They require human management, electricity, liquid nitrogen. They're susceptible to climate change, disease, geopolitics. When you think of something that needs to last for hundreds or 1,000 years, there's a lot of unknowns and uncertainty. Case in point, the Svalbard seed vault did flood a couple of years ago. The seeds were okay, don't worry. But this flooded, and it was a little bit of a warning sign to say we need to maybe think a little bit more creatively about backup options. There are a few other kind of confluence of factors that lead us to looking at this. One is advances in cryopreservation. We can now take skin cells from animals, freeze them, thaw them out, transform them into sperm and eggs, and recreate whole populations. We can do that today. And I'm told that the implications for humans are a few years from now, a lot of interesting ethical questions. But a lot of advances. The lunar environment, as I mentioned, is ideal for the temperature profile. And of course, a lot of missions upcoming to the moon through NASA's commercial lunar payload services program. There's several companies with landers now. The moon seems to be like it'll be becoming a lot more crowded, and so we can take advantage of that. So that all leads us to this concept to create this passive long-term storage solution for animal cells, starting with animal cells, but doesn't necessarily need to stay, could be expanded for all of Earth's life. Long-term, I like to put a round number on this, over 1,000 years in passive storage, so no powered thermal or other mechanical systems. This concept was described in a paper that came out about a year ago. And as far as science papers go, this one sort of went viral. It's been named one of the Smithsonian's top 7 scientific achievements last year. There were more than 200 interviews and articles. And as far as when I talked to Smithsonian PR, they told me that we don't get this kind of attention unless there's like a baby panda involved. So we've sort of reached this baby panda level of engagement on this, which it just tells us that this resonates with people, and it's something we're looking to expand on. From an engineering view, I like to break this out into 2 types of problems. There's the getting there, which all the integration in the launch vehicle, all the life cycle phases, the thermal cycling, the different radiation environments that you go through from here to the moon. And then there's the staying there, the materials and the excavation and the radiation protection that you would need to survive for longer than a 1,000-year timescale. We've been focusing mostly on the getting there part so far, and have designed an initial conceptual design for a payload that could demonstrate some of these technologies to maintain temperatures throughout the mission profile. So that's been the focus, but we're also, of course, trying to design the overall concept. One other angle here, and the place that we might want that we're trying to start from, is preserving Earth's biodiversity doesn't show up in any of the decadal surveys or the roadmaps or space technology portfolios. But what does show up is cold storage and transport needs. And so if you can bring frozen samples from Earth to the moon, you could imagine a multi-purpose platform that could also return samples back from the moon. And so that's the place that is prioritized. And I've talked to, most of my career, it was at NASA in Houston and in the Bay Area there. And so we've talked to several people. That might be the place for something like this to start to build a capability. And I'll just mention that there's many different types of this that are non-technical, that are governance-related sensitive topics. Something like this requires a diversity of thought. And what we're moving towards, what we want to do in December, is this future scenarios workshop. We're going to bring in science fiction authors, futurists, scientists, engineers, to help us define these scenarios. These are constraints that we can use in the design process. So that's a kind of an interesting way to bring the community, but also to set some real constraints and assumptions we can build around. So to conclude on this opportunity, this is a long-term mission for all of humanity, really all of life on Earth. It does connect to this NASA and other private companies' goals to ensure survivability, not just about ensuring that humanity is a multi-planetary species, but also that all of life is considered in that. There are interesting science goals in studying the evolutionary processes when you put cells in long-term in these space environments. It supports human space exploration as you think about ecosystems and biomes and all the different life forms that we're going to need to bring for settlement purposes. Creates new avenues for collaboration. And it's interesting for the Smithsonian because we have this wide network of sample collection, data management, cryo storage. So all these reasons make it interesting for us. Challenges, there are many, of course. This relies on infrastructure, capabilities that just won't be there for some time. I mentioned it's not currently prioritized in the decadal surveys or portfolios. There's also this big disconnect between what can be funded in the near term and what will ultimately be needed to realize a long-term vision. There are certain groups that hold the moon as sacred ground. And so we want to be sensitive to those groups and also to engage with stakeholders early in the process to make sure that we're considering all those perspectives. And then this one's a little bit more philosophical. What we're really creating here with is the book of life, and who owns, governs, manages, something like that. There's a lot of questions here in a concept like this that we need to talk through. Okay, and then the last piece of this is, as the Smithsonian, we're known for our museums. We're known as being caretakers of the past. And something I like to think about when we think in the future, what if we were also known as creators and facilitators of the future? In some ways, there's no better people than the caretakers of the past to connect that thread to be involved in helping to shape the future. And so this is something that, in general, we're interested in at the Smithsonian. I will mention that this concept is really interesting. We have had no funding yet for the design, so we're interested in partnerships and hope to start building on this concept. Okay, so my last piece of this is about this concept of the impossibility frontier. So I'm going to zoom us back out a little bit and explore what is, I think, like a deeper cultural roots of this idea about frontiers and why I believe the impossibility frontier matters so much today. So please forgive me. Let me just, oops. I think I pulled out of that. So forgive me that this is going to be just a little bit more of like a poetic note. But when I think about impossible challenges, if you're like me, I'm sure you're probably a space nerd. You think of Apollo, you think of the moon landings. And in particular, I think about this phrase that's been like lodged in our cultural psyche. If we can land on the moon, why can't we ... cure cancer, solve climate change, end gun violence, fix public transit, etc. This phrase has become a part of our collective vocabulary. It's been around for more than 50 years, and it's come to mean anything is possible. And depending on your mindset, this phrase can either be deeply hopeful, like a rallying cry. We did this, just imagine what else we can do. Or it can be deeply cynical, a way to point out a dysfunction. Like, sure, we can land on the moon. We can't even get this printer to work. Come on. And fascinated by this phrase because I think it's so fundamental to how we see the world. It highlights possibility on the one hand, but also something that's potentially dangerous on the other. Because if left unchecked, cynicism can become the song of the prisoner who has come to love his own cage, according to David Foster Wallace. And so I want to figure out how we can bring back that earlier mindset, that anything is possible kind of spirit, not as a naive optimism, but as like a generative force. Because a world where anything is possible is a world full of wonder. And I really think that we could use a lot more wonder in our lives. Now, if we go back a bit in time in history, the sense of the moon or space as a symbol of possibility, it isn't new. It certainly wasn't new during Apollo. In fact, for over a century now, Americans have used the idea of the frontier to define who we are. Right? In 1893, Frederick Jackson Turner, who is also an alum of the University of Wisconsin-Madison, that's where I did my undergrad, he argued that the moving Western frontier shaped the American character, that it made us more innovative, more self-reliant, more pragmatic. And so even after the geographic frontier closed, the metaphor didn't. It kept going. We kept using it for space, for science, for civil rights, for technology. In the 60s, Kennedy called his vision for America the new frontier. And of course, space eventually became the final frontier, just a powerful metaphor. Of course, it wasn't perfect. The traditional frontier myth, especially in American culture, was often about conquest, right? It left out a lot of people. It erased some people who were already there, celebrated rugged individualism and expansion. And this sometimes came at the cost of justice, of community, and collaboration. So what I'm getting at here is I think we need a new version of the frontier, one that takes the best parts, the curiosity, the audacity, the drive, and lets go of the baggage. One that's more open, collaborative, inclusive, more longer term thinking, rooted in stewardship and awe and grit and wonder. And so I think instead of a singular moonshot, a true frontier is more like a continuum, a constantly evolving wave of progress that we push outward simultaneously along many fronts and together. Of course, you don't need to work on lunar payloads or Earth-sized telescope to push on a frontier. The impossibility frontier can show up anywhere. Wherever someone is working to expand what's possible, using wonder as a catalyst, driven by a clear purpose, focused on the long term, seeking collaboration over conquest, and intentional about designing the future, I think you're out there on the frontier. So that's kind of conceptually what I mean by the impossibility frontier. If we think about it a little bit more visually, this is where most humans like to be. We like to be in this comfort zone. It's nice in there. It's warm. It's cozy. It's familiar. Land of best practices and reliable outcomes. And when we venture out of that, we go, let's call this the discomfort zone, where things get a little dicier. We don't really like to be there. It's hot, sticky. It's like Houston in August, right? It's not that pleasant. It makes you question your life choices. And I only say that out of love because I used to live in Houston. But here we're up against this natural force that's not so unlike gravity. That's pulling us back. It's pulling us back to this comfy air-conditioned home. So why do we venture out anyway? Because somewhere out there is this line of what is actually impossible. But we don't know where it is, right? Not really. What we do know is that if we push through, beyond discomfort, there lies something else. Wonder. And this is absolutely fundamental to who we are. We are pulled outward by this equally impressive force to seek out that wonder. And the truth is we can find wonder everywhere, not just in the grand or the cosmic, but in the overlooked and the everyday. I see it in my kids' eyes. These are my three boys. And I see it when they learn something new. I recently took them fishing, and the wonder of that day was just how wiggly the worms were, right? They couldn't believe it. Their minds were just blown. And so, wonder isn't rare. It's just waiting for us to notice it. But if we want to live in a world where anything is possible, we have to intentionally design for it. And if we want to create a world full of wonder, not just fleeting moments, but lasting systems of awe, and this is coming from my view as an engineer, we need to engineer it. And that means taking on impossible, long-term, purpose-driven challenges. So the comfort zone is where we operate. The discomfort zone is where we grow. But the impossibility frontier is where we transform as individuals, as teams, as society. And more than that, it's where we create wonder. To close this, I think space projects play just a really unique role in all this, especially at the societal level, because nothing else, no other domain but space, comes anywhere close to the wonder that the sheer vastness of space and our relation of our size to it, our feebleness and our brilliance can create in us. Space is like a catalyst for wonder. It's not the only domain within an impossibility frontier, but it is the one that should lead the charge. And it's why this phrase, if we can land on the moon, is so powerful. The moon is this constant symbol in our lives. It's up there in the night sky. It's reminding us of frontiers, this beckoning for wonder. And so to me, what's really remarkable about NASA or any really truly ambitious space project isn't a flag on the moon. It's this indelible, insatiable desire to live out there on the impossibility frontier, to be a flywheel of wonder, to have the audacity to imagine a world where going to the moon wasn't absurd, but just impossibility waiting to be engineered. I know all of the practical reasons to explore space, survival, science, sustainability, security. I love all those reasons. They're all great reasons. But for me, my why for space is to create a world full of wonder, to inspire people to confront their own impossibility frontiers, and to live in a society that finds it utterly inconceivable to step up to a frontier and to back away.
Great. It was a great final speech there. I'm going to take the liberty of asking the first question, but there's a bunch of questions in the chat that maybe you can see or we can get to, or maybe Lydia can manage them. But okay, it looks to me like the Next Gen Horizon Telescope is not exactly in the impossibility frontier. It's kind of an engineering extension that we think we can do. And the moon biobank seems a little bit more in the impossibility frontier, a little bit more spiritual, a little bit less developed, a little bit more iffy. The telescope is like you got your international partners. It's kind of a matter of just securing the funding and doing the work. Okay. Now, I want to say something, Mike. I will get to a question. The last stuff you said about if we can go to the moon and this sort of spiritual nature of space activities, that's a very powerful thing. But on the other hand, the moonshot Apollo program was a different thing, arguably, than what our common contemporary vernacular calls moonshots. Actually, we pretty much knew we could do it. I had to develop some technology and do some hard work, but it was not like, oh, this is impossible. You could never land humans on the moon and bring them to Earth. But people knew fairly quickly that was possible. So I think it's an interesting thing to try and disentangle, because things are truly impossible. There's no point in doing them. If they're hard, then they might still be just a logical extension of the comfort zone. It's a strange thing. I'm not quite sure can you actually objectively by something that is in this magic realm where it is spiritually and technologically meaningful and yet not just outright impossible.
Yeah, I think that's part of what is amazing and beautiful about it, is to try to really figure out, we don't actually know, in a lot of cases, we don't actually know where that line of what is actually impossible is. And it's part of the journey in trying to define it, to take on these challenges, to figure out where that frontier actually is. Of course, there's certain things that we just, we know are impossible right now by the laws of physics, but we don't really know where that frontier should be. And every project like this, these are space projects, and I certainly see a role for space as this catalyst. But it's not just limited to space. I think anything that kind of stretches us along these right dimensions and meaningful dimensions is worth pursuing and worth considering as part of this alternate view of what frontiers actually are. But yeah, I think you're right. If you look at it objectively and is it data driven, is this possible? Is this impossible? Where's the line? I think we're talking about a lot of gray area in that. It's more the spirit, the meaning behind it, I think.
Great. I think Micah had a question. You had a couple, Micah, but maybe choose one for now.
Sure. So the Earth is spinning, the Earth is rotating around the sun's rotating around the galactic core. How much of an impact does all that movement have on actually getting useful data out of the telescopes? Is it pretty insignificant, you can mostly ignore it, or is it one of the really hard problems trying to account for it all?
You say that again. So the movement,
the
act that we're rotating, we're moving as.
The fact that all our telescopes are moving relative to the object they're trying to take a picture of, and the Earth is rotating, so the angle the telescope is having to change. Is that a big problem, or is that something that's easy to solve and kind of ignore for the most part?
Yeah, I wouldn't call it easy to solve, but from the Earth rotating and the movement through space, it's fairly known. We can calculate that. We know where the telescopes are and where they're moving to. We know GPS positions of the telescopes, which matters in this actually. And so we can calculate and get best fits of data based on that. As far as if we're talking about visual imaging something much closer, then these things are so far away, they're coming to us essentially as a line wave. It's not like a propagating circular wave by the time it comes to us. So we can treat it all as flat. So in that sense, the relative motions, within the Earth are very small compared to those larger range structures.
Anthony asked, to what extent are the system's initial scientific requirements set and agreed? And are requirements constantly changing? Is it in the design space or the requirement space that all the changes you mentioned, algorithms, number of sites, etc., are being explored?
This is a great question. To what extent are the overall requirements changing? And part of what we use in a systems engineering driven process is this. It'll look linear in a design flowchart, but in practice, it's not actually linear. It's very iterative. So in practice, what we did, we got 8 different science working groups together representing the community interest in various science goals. They duked it out. They wrote papers. We figured out what requirements were needed. And there's an iterative process with what's possible on the engineering side and what the science ambition is, and a process to define what those goals are and what the measurement is needed for those. At some point, though, we have to move on as the science goals will continue to evolve. You have to draw a line in the sand and say, okay, for these goals, here's what you need. And this fits in the constraints of what we think is achievable for cost, technical, we know our instruments can do. And so at that point, then you set the requirements. The next stage, you set the initial design. The next stage, you set a final design. And as you learn things about algorithms and imaging, that does help, but at some point it needs to get locked in. Otherwise, you wouldn't build anything. And so I think that there's a linear and an iterative nature to your question, but ultimately we try to use these processes to make design decisions.
Thank you. Carol, I think you had a comment/question. If you'd like to share that.
Yeah, maybe it was a comment, but seems to me like the requirements for your biology package are similar, not similar, but they're at the same place or could be at the same place as your telescope, because basically the telescope requirement, as I understand it, is to have a very long baseline. And putting a radio telescope on the moon has been discussed for many years. So that would be a much longer baseline. Once you start having stuff you're doing on the moon, it's not that hard to have more stuff that you're doing on the moon. So
Right.
Why not combine those projects?
Yeah, it's a great concept. It is something that has crossed my mind, and something I've discussed with the scientists here is to think about the infrastructure and the activity that could be possible on the moon. It makes us think we're used to thinking of the moon being remote and not a constantly visited thing, and it's likely that it's going to change. So I agree. There are some science limitations with the baseline. Like longer baselines give you better resolution, but you actually also need the shorter baselines to see the larger scale structure. So you need this mix of short and long baselines, and you also need the ground array and the instrument on the ground that are available at a much more regular rate. So there's a lot of pieces, but yes, moon would be a great place to put a telescope, or maybe an array of telescopes, and that's another concept that's been kicked around.
One other question I had, and someone else echoed it, is why with the telescope do you have to fly the data on an airplane? That kind of puzzled us.
Yeah, it turns out it's still actually faster and cheaper to be able to ship these ship the data by hard disks on planes, bring them to a central facility. A lot of times you also have to wait for some of the data, like in the South Pole. You have to wait for summer to fly out of there. So if you're going to wait anyway, that's another piece of it. But it's still cheaper to be able to ship by 747 or other aircraft than it is yet. That could change in the future. But for these amount of data, you can't reduce the data at the site either. That's the other piece. You have to send all of it, and all noise and all, to the correlation process.
So you can't put it on the internet. It's just too much data.
It's too much. I mean, you could. It just would be slower and more expensive to do it that way than it would just for the amounts that we're talking. For now, maybe in the future that'll change.
Awesome. I think the next question comes from Tini AV.
Yes. Hello, hi, thank you so much. You touched on governance at the very end of your presentation. I'm a space governance expert, but I was particularly interested in the last answer you gave about the systems engineering approach and having to just end up getting things done. And so because of that, I actually joined one of the working groups for this project, the one on social science and responsible siting. So it was very interesting trying to see, okay, humanities and social sciences, how do we get our perspectives into these projects? And so even though obviously we are like a legitimate working group as part of this whole collaboration thing, is it still always just going to be just like an aside, like the last slide you give at the end of your presentation, kind of like, oh, and there are these other considerations too. So how do people actually meaningfully engage and think about these non-technical aspects? Thank you.
Yeah, it's a great question. The systems engineering process should be considering more than just the technical aspects as we start moving through a design process. And it shouldn't be an afterthought. It absolutely isn't meant to be. And it's something that's one of the reasons we have that working group that you're talking about. But I think we could do a lot better to have more communication, more touch points. It's certainly, as we start thinking of new sites, we've done studies for different sites. We've done stakeholder meetings. We've sent people to just on fact-finding missions, really just listening that's the first step. What we don't want to do is kind of recreate some astronomy issues that have come up where some elite university coming in and setting up place without talking and discussing this with the groups that have a strong interest in it. So it's important. We could do better, and let's chat more.
Great. Did anyone have any other questions?
I've always got more questions, so please stop me. Two fairly related questions that are hopefully short answers. Why put telescopes on the surface of planets instead of out in space? And why put frozen things on the moon instead of in space? Feels like both those would be simpler just in space, like orbiting.
Yeah. So what's interesting is there is a separate project to put a telescope in space as well, but you're also limited in the sensitivity of that dish, just because it's not going to be a very large dish. So you're above the atmosphere, so you can access different spectra that are possible from the ground. That's a good thing. You can improve your angular resolution, longer baselines, but a space telescope is still reliant on the ground array for the sensitivity and the overall coverage, like filling in the whole UV plane. So there's aspects that, yes, space is interesting. It helps us particularly in being able to image and learn about the photon ring, but it doesn't, do things like with the jets. It's much better, not much better, but it's probably more important to have the ground array as well. So both of these kind of work in parallel. As far as the space versus moon, it really comes down to temperature. If you could protect and get the cold temperatures and stay out of the sun, then you could imagine a biorepository in space as well. We happen to be looking at the moon because there are these regions that stay dark and they stay cold forever. And so that's the main piece. Radiation is a major issue here, though, because we need to essentially use a lot of regolith to be able to protect it for a long time. So lots of challenges there, but space not yet, because of it also gets hot in the sun.
Thank you so much. I think that's all the time we have for questions today. But again, thank you, Garret, so much for coming on the group. It was really great to hear what you're working on, and thank you everyone else for joining us. And we will see you next month.